We're recording. All right. So
anyone who's watching this recording.
Okay. All right. So let's get a bunch done. The first thing I want to do is I'm going to tell you what kind of the agenda is. What I want to get done, because we get off, not off topic, but you know there's a lot of people, a lot of questions and stuff, and I keep trying to get behind where I need to be. So what I want to do first of all is we're going to learn how to use Kepler's laws to solve some problems about planets going around. And then, and then we're going to see a program that I wrote that will simulate Kepler's laws, except there's something about it. I can do all parallel weird universes with it. And then is the question, why? Why should Kepler's laws be true? And that's where we talk about Newton. So the first thing I'm going to do, there's going to be some math. Have a calculator out. If you got one. If you don't, get ready to use your noggin. You got a noggin?
No.
These things?
Not anymore.
No.
I have a computer which is basically a calculator.
Okay, other than, I'll tell you what, listen, here, use this.
Okay.
Because,
Can you run?
I got it. Yeah, I don't really want computers open when everybody's just So first of all, here's some mathematical statements that mean stuff that you should understand. This one right here that I'm about to write is kinda sorta obvious. I don't know. Maybe we're a little bit lucky that it works, and that's that the average distance from the sun is the average of the closest and the furthest, or the furthest and the closest. Here's the context. This is an orbit. It's elliptical, so says Kepler. The sun is at one focus of it. I've done a rather extremely elliptical orbit, but in this case, you can clearly see the closest it ever gets is the perihelion. The furthest it ever gets is the aphelion. The planet goes around like that, you know. And the average distance from the sun is simply defined as the average of the closest and the furthest. So that's easy, isn't it? That's easy. What else do I have to say? Here's something I did not teach you yet. I'll teach it to you right now. You know, when you draw an ellipse and you do the thumbtack thing, like when you take your two thumbtacks and you stretch the string out, you draw the ellipse like that, and these are the foci. There is a parameter, a number, that tells you how elliptical the ellipse is, like how non-circular it is. The word for that is eccentricity. It is defined, well, eccentric means off center, and basically a circle, well, put it this way. Finish this word analogy. Circle is to ellipse as square.
Is to rectangle?
Got it. I couldn't even get the words out of my mouth past my mask. There, you nailed it. Did everybody get that? It's like a circle is a special case of an ellipse. In fact, Kepler did not say that orbits can't be circular any more than you would say that rectangles can't be squares. But the vast, infinitely vast majority of rectangles are not squares, right? Because it's a very, very special case. So circles are okay. But guess what the eccentricity of a circle is? Zero. Circles aren't eccentric at all because both foci are in the same place. So the eccentricity of an ellipse is a function of how far apart your thumbtacks are. If your thumbtacks are together, the eccentricity is zero. Then you get them further and further apart, it gets more. Here's how it's defined. It is defined as the distance between the foci divided by what I'm going to call the major axis. Now, an ellipse has a major axis and a minor axis, and I think that's kind of easy. Yeah, this is the long diameter is the major axis, and this is the minor axis. And I'm not going to worry about the minor axis. Hey, you know what? One way you could have defined eccentricity, could have done this, could have just said it's the ratio of the major to the minor axis. Personally, I think I'd have done that. You see what I mean? Then a circle would be one, because they're the same. That's not what they did. They did it this way. And here's what it is. Eccentricity is this divided by that. Now let's do that in terms of perihelion and aphelion. Eccentricity, E, that's eccentricity. You know there's another focus right here, but I don't worry about that just yet. Can you tell me how to express the major axis of the ellipse in terms of these two things? What is it, Rhea?
Aphelion plus perihelion?
Absolutely, because it's the whole way across. And you're just looking at the picture. You can see all the way from here to here, then to there. Aphelion plus perihelion. Everybody's got that, right?
This
Is that pretty clear?
Yeah. This is going to be on Power School, right?
It's in my handout that you read,
And that works too.
okay, yeah, an Astro handout. What about the numerator? That's the denominator. The numerator is going to be this distance between them, and notice the symmetry. You see, this is also the perihelion, even though there's nobody there. That doesn't mean I can't draw it. I drew it. So this is the perihelion. So you know what the distance between the foci is?
The aphelion minus perihelion.
You got it. So all you do is this. To find the eccentricity, it's the aphelion minus the perihelion divided by the aphelion plus the perihelion. What do you think the biggest eccentricity possible is?
1.
Yeah. In fact, if you ever reach 1, it's technically not an ellipse anymore.
Circles. It's a line.
It's a parabola.
What? Pretty close.
Yes.
It's a
And if you
line.
go beyond that, it's a hyperbola. But don't worry too much about that right now. Let's just say they all have one less than 1. It's anywhere from 0 to just barely under 1, like 0.999.
So a circle is 0.
Circle 0.
What is
Circle
that?
0 because the two are together and the aphelion and perihelion are the same and the numerator is 0. Yes?
What is a hyperbola?
It's eccentricity. I guess it's greater than
I don't know.
I got to
what it
think
looks
about
like.
that. Are you going to learn about it later?
Okay.
So far so good? Now let me write something else up here. The other thing I want to write is this. Okay, look. You remember Kepler's mom's apple pie? Yep, like this. Now, notice this is Kepler's law of what? What law am I talking about when I draw this stuff? Areas. The law of areas that says the line drawn from the moving planet to the sun sweeps out equal areas and equal time intervals. Now, to find areas, you generally multiply lengths times widths, don't you? Kind of. I mean, maybe it's a triangle and you do a half in there or something like that, but generally, areas are this dimension times that dimension.
Right.
So something like an area, now by the way, if I pick certain times, then you know, like this here is the speed. When I say V sub pH, I mean the speed the planet is going at perihelion when it's closest to the sun. That's the speed it's going. But you know, if you multiply a speed times a time, what do you get? A distance. So this is like a distance. And this is like a distance here. And what I'm trying to say is, this thing I'm about to write, V sub pH times the perihelion, the speed it's going when it's close times how close it is like an area. Don't fret too much about the fact it's not really an area because there's not a time in it. But it's kind of an area-ish thing. And guess what it equals? I bet you can tell me.
1?
Come on.
Oh, GH.
That's what I'm saying. I'm saying that the product of how fast it's going when it's close times how far it is when it's close is the same as the product of how fast it's going when it's far times how far it is when it's far.
So that's the mathematical way to express the law of areas.
Yes. This is a way. It's not the only way. It's not the best way. It's the way I want to do, though.
Wait,
So,
then why are you teaching us the best way?
because the best way would involve vectors and signs and things like
I
that.
love vectors and signs.
There you go.
Well, I don't.
Much better than constellations.
Okay. No.
You know, if Vector was so cool, he would have stolen it.
All right. It's kind of It's kind of the law of areas. It's a consequence of the law of areas. And now I'm going to write another law. I'm going to write the law of, well, I kind of got the law of elliptical orbits drawn. I kind of got the law of areas said, but now I'm going to write the law of what?
Period.
Periods. And the law of periods is this algebraic truth that Kepler empirically found by staring at some numbers and figuring what's the pattern and deciding to use algebra to model it. And so here it is. It is t squared equals a constant times r average cubed. I will elaborate. We will practice. We will get good at it. Okay, so t means what?
The period.
A period. What do we mean by the period of a planet?
How long it takes.
How long it takes to finish an orbit. Got it? What units are good to measure it in?
Years?
Years are good. Days,
Light
hours,
years?
seconds, whatever
Light
time
years.
units.
No, not like.
I think I like years the best, and I'll say why. And then R average, oh my goodness, we were talking about R average up here. It is the average distance from the sun. You could also say it's sort of the average radius of the orbit, but that's what kind of an expanded idea of what radius means, because usually the radius is a circle, but I'm kind of extending it here. It's like, okay, so it's not exactly a circle, and the sun's not exactly in the middle, but there's still like a distance, right? Like a radius, and there's an average.
So like major axis plus minor axis over 2.
That is what it is.
Okay.
Well, actually, yeah, you said over 2.
Yeah.
You know, I hate to say this, but it's over 4.
Wait.
Because it's the semi-major axis. And see, the major axis is the whole way across. It's like a diameter. You just gave me a thing for average diameter. Radius is half the diameter.
Yeah, I do that a lot.
Yeah, that's okay. Okay. All right. Now, what are some good units for distance? You could use miles or inches, but AUs. And an AU is the average distance of the Earth from the sun. In fact, I tell you, if we will use, and we will, mostly, if we will use years for the period, and we use AUs for the radius, then one of the example planets is yours truly, sort of, Earth. And the Earth is how many years to go around the sun?
1.
Yes, and how far is it from the sun?
1.
1. So 1 squared equals something times 1 cubed. And what is the something?
1.
1. If you're using those units. So let's use those units, because it's nice to have a constant of 1, because you don't have to put in your calculator.
1.
Yeah, so let k equal 1. Let k equal 1. There. This stuff we just wrote, we're about to use. So here we go. Let me make it, I know, I like it when you work a problem backwards and forwards. Inside out, every which way around. Because when you see it, like in other words, you know how a problem has given information and asked for information? You could make a new problem by giving some of the stuff you asked for before and asking for some of the stuff you gave, right?
Right.
Okay, let me do it this way. What if I just flat out tell you that some planet has a perihelion distance of 3 AUs and an aphelion distance of 4 AUs? And maybe I'll tell you that at perihelion, I'm just making this up, it's going 10,000 miles per hour. I just made that up. Maybe that's not right, but I just made it up. Figure out everything you can. What all can you figure out if I tell you those things? I told you the perihelion. I told you the aphelion. No, except I don't like my aphelion. I'm sorry.
You should be.
I want 5. There we go. I like 5 better.
Mr. Edberg, is
Yeah.
this stuff is going to be on the test, right?
Yeah.
Yes.
Oh, thank God.
This question.
That's so much better than learning about
Yeah, can we
cosmos.
just put this question on the test?
Oh yeah.
Yeah, I'm so much better at math than I
Oh
am.
good. It's your stuff.
I'm so
Enjoy.
scared.
Enjoy.
I am.
Excellent.
I hope we never go back to
This is
sidereal days.
Part and parcel of what we
Wow,
do.
I found this
And so
We can find the eccentricity.
Yeah, you ought to be doing this, you ought to be getting it quick, and you ought to have most of them done about now.
I do not have.
I don't know.
Some of you hardly even need a calculator.
I do not see 30 divided by
I'm
5.
confused.
Yeah.
Okay, tell you what.
Beautiful.
Let's see if you've got our average figured out. What is our average? 4, thank you. Indeed, this is going to be, 5 plus 3 over 2 is 8 over 2. Makes 4. 4 what? 4 AUs. The average distance is 4, if it gets as close as 3 and as far as 5. You with me so far?
Mm-hmm.
Oh, yeah. Eccentricity.
0.25.
I think so. It's 5 minus 3 over 5 plus 3. That's 2 over 8. Yes, it is. It is 0.25. That is a, you know what, that's actually a pretty big eccentricity for a planet, but comets tend to have bigger eccentricities than that. So it's a noticeably misshapen with sun off center orbit. Not quite as much as the picture I drew, but still significant.
Yes, sir.
You can see it. Yeah.
So does eccentricity get smaller with more mass? Or?
No, well, the things that cause something to have the eccentricity it has are many and varied and contingent and who knows, like that.
So there's no fundamental.
Yeah, well, now there is something I will say. There is a reason why comets have extreme eccentricities. Heck, I'll go ahead and say it.
Okay.
It's because generally they have, accidentally encountered the king of planets, Jupiter, which just near about slingshotted them out of the solar system, but not quite. And so they got sent off into the deep, dark depths of interstellar space almost, and then whip in near the sun. And so they're in these big, long orbits, and they're very eccentric. Most of the planets kind of formed already in orbit around the sun, and they got no reason to have really badly misshapen orbits. Comets have been messed with.
Yeah.
So there's a reason. Okay, now, how about this one? What could I possibly ask for? Well, maybe the one thing I didn't give, right? Maybe the speed at aphelion. So it's I know the perihelion is 3.
So it's 30,000 divided by 5, whatever that's supposed to be.
Yeah, it's 6,000, right?
Okay.
So it's 3. That's all right. No, this is 10,000, and this is 3, and this is 5. And so you do 30,000 divided by 5 makes, here it comes, 6,000 miles per hour. So what I'm saying is the planet goes slower out here than it does here. It's going 10,000 miles an hour here, and it's only going 6,000 miles an hour out there.
Only.
Only.
A casual pace.
A casual dawdle.
My walking speed.
Now, how about the period?
8 years.
It is 8 years. Didn't I pick nice numbers? That doesn't usually happen. There's only a few examples of numbers where some number's cube is equal to some other number's square. Yeah, you like that, huh?
There's some good numbers.
Really
good numbers. I appreciate it.
I'll tell you another good one. 100 cubed
Okay.
is 1,000 squared.
Yo.
Okay. All right, it's not that. Good.
Wait,
So anyway, I knew that one already. Okay, so you've now found out that the period is 8. That's because if you take 4 and cube it, that's 4 times 4 times 4 makes 64. And what mystery number has a square of 64? Why, 8 does. So look what we figured out. We figured out that if a planet varies from 3 AUs to 5 AUs from the sun, the average distance is 4, the eccentricity is 0.25. It goes 3/5 as fast at aphelion as it does at perihelion, and lo and behold, it takes 8 years to go around. Now, what if I switched it up on you? What if I, say for example, withheld from you the aphelion.
That's not nice.
What if I withheld that from you? Then I would need to tell you something else. Maybe I would have told you the period was 8. Maybe I would have said the period is 8 years.
So then you just
Sorry,
go
Linda.
backwards.
Yes, indeed. So can you work backwards right now? Can you figure out how to figure out the rest of it, given the period is 8? What are you going to do with the 8?
So square root the 8. No,
Well, you will
the
square the 8.
Square the 8, and that's 64.
Then what do you do to get your 4?
64 cubed. No, wait, no, cube root.
Someone's got a nice image of the sun going up here. It's Jason's.
Oh, that was the
Watch.
sun.
Oh.
Yeah, it was a nice picture of the sun, actually.
I got very.
So do y'all understand? Do you know how to use your calculator to square things, cube things? Can you take a square? Can you take a cube root on your calculator? You know how to do that?
Yes.
You can practice right now. You can take 4 and you can square. Sorry, no, you can take 8 and you can square it, and you better get 64. And then you go like 64 uncubed, or cube rooted.
Oh, cube rooted.
Personally, I tend to raise things to the 1/3 power to do that, but there's different ways. Take the cube root of 64 and your calculator better say 4. And once your calculator says 4, then you go, aha! I know that the average of 3 and mystery number is 4.
So then multiply 4 by 2
And subtract 3 and you got 5. And then you can do the rest of it. Now, I'm not going to spend a long time practicing these things. I think you can see what kind of application I'm talking about, right?
Yes.
And I do have a problem in the homework, in the ones I made up, and there's also 1 or 2 of the ones from the book, that use exactly these things. So I'm going to expect you can deal with that. And then you get to practice it for homework, and I'll call that good. What I'd like to do now is jump into some application of it. So here's an application of this stuff. I love it when they send stuff to Mars. And Mars got flat out attacked with stuff recently. My gosh. The U.S. sent a rover there to land. China sent a rover there to land. Some other people sent. We're sending stuff to Mars. And how do you do that? Now, the thing is that this would make more sense a little bit later, but I'm going to go ahead and talk about the plan for how you send something to Mars. So what do? Here's the thing. Us and Mars, we're both going around the sun. Here's the Earth going around the sun. I'm going to simplify things and say that the Earth is 1 AU from the sun. Well, it is. Oh, but it varies, right? From like 0.98 something to 1.01 something.
At
So
this point in time, it is 180.
yeah, when I care about it, there it is. Mars varies in distance. However, I feel like making a relatively simple. Now, you know what? Yeah. I'll make it relatively simple for the time being. Let's just say that Mars is 1.5 AUs. It's really 1.527 on average and ranges from 1.38 to 1.67, something like that. It varies, but let's just keep the numbers easy. These are easy numbers. So the question is, how do you go to Mars? Let's talk about some of the issues. One is, here's an idea. I'm gonna like throw out there successively better ideas. Each time I come up with an idea, you tell me something that might be wrong with it. Okay? Here's idea number 1. It sounds like a good idea at first. Here's the Earth going around. I think I'd wait till Mars is at opposition and aim a rocket at it. Ready? Aim, fire, and shoot a rocket at Mars.
But you'll miss.
Yeah.
Why would I miss?
You gotta wait till they intercept.
We're moving.
We're moving fast.
So's it. Hey, you know what? Y'all kind of like brought up 2 things at once. I thought maybe somebody would say, no, nobody did, Y'all caught this right away about us moving? I thought maybe somebody would say, oh no, you're trying to hit a moving target. It's moving, so it won't be there when the rocket gets there, right? That's like a quarterback trying to throw a pass to a receiver and being dumb enough to throw it at where he sees the receiver instead of where the receiver is going to be by the time he receives it. Do you understand why that would be an issue?
Yes.
Okay, so yeah, and you'd be afraid of maybe aiming at it and missing like behind it. But y'all actually saw something else going on. This quarterback is running. The earth is moving. In fact, the earth is moving faster than Mars. If you were the quarterback and you're running faster than you and the receiver are both running this way, but you're running faster than the receiver, you actually might have to throw backwards a little bit, right? They do stuff like, oh, have you ever seen Australian rules football? Oh, they're like punching it and doing all kind of goofy stuff. There's like 6 goals, and these referees in pinstripe suits with hats go, it's like, what am I looking at? Okay. Anyway, so do you understand? You got the issue of the things moving, but there's another problem. Due to like gravity or whatever it is makes planets do what they do, your spaceship is not going to go in a straight line. Well, not, maybe if you shot straight out, but basically, you know what your spaceship becomes as soon as it's free from the Earth? A planet. And you know what laws your spaceship is going to obey?
Planet law.
Kepler's laws. So basically, when you fire a spaceship out into interplanetary space, it is in orbit around the sun obeying Kepler's laws. It's going to travel in an elliptical orbit with sun at one focus. Now there are issues about the gravitational pull the Earth has on it and the Mars pulling on it, and yeah, those take into account. But for most of the trip, it's a planet. Yes?
Actually, I'll wait until this is.
Okay, for most of the trip, it's a planet. So what you're going to do, it's going to be on an elliptical orbit, and you want the ellipse to connect the orbits. Now, there's a lot of ellipses you could do. You could do this ellipse. You could shoot it real hard and make it go fly way, way, way out, God knows where out here, and come in like really close like that. You could send the spacecraft onto a stupid elliptical orbit that takes enormous amounts of energy. But you don't have enormous amounts of energy. I know SpaceX and all that, lots of energy. But I mean, you don't want to use any more energy than you have to. There is a minimum energy orbit, one that is the cheapest way to get someplace. Not the quickest, but the cheapest. Do you know what it is?
Is it like the angle is around 30 degrees?
No.
Is that what it is?
It's where you connect the two orbits with an ellipse that has the Earth at perihelion and Mars at aphelion.
But it takes a while.
It takes a while. That's what we're going to figure out. But that's the best thing to do to save money and energy, which you can barely afford energy and money-wise to even get anything there in the first place. You need to do something like this. So what you do is you launch it in such a way with such a speed, and we'll talk about the speeds later and everything, but you launch it in such a way that it will be on an elliptical orbit that, if allowed to continue, would periodically, with a period T, revisit the Earth's orbit, revisit Mars' orbit, revisit the Earth's orbit. But of course, the idea is you hope somebody's home when you get there. Like, you go on some big, like you're planning a big trip, like you're going to do a cross-country, round-the-country big driving trip. I've done that before. And you're going to go all the way to Oregon. And you're thinking like, wow, I'm in Oregon, I'll see my relatives in Oregon. Maybe you should call first. What if they're like also on a big trip and they have to be in Michigan when you're in Oregon, right? Then you missed, right? So the thing is, you got to plan it right. You need to launch from Earth so that when you reach Mars' orbit, guess who's there?
Me.
Mars. That means you can't just do that. You can't just do this any old time, right? You got to do it at the right time. Let's talk about that for a minute. First of all, tell me the perihelion and aphelion of your spaceship's orbit. You can see them. What's the perihelion? Yeah. The perihelion is 1 AU. The aphelion is the 1.5. Right now, please figure out the period. Find the period. Do it with your calculator right now.
I got it.
Find the period of this orbit.
Is it 1.25? I really hope so, or else I learned nothing.
Well, our average is 1.25. You're off to a good start. I mean, you do want our average, and our average is 1.5 plus 1 over 2 is 1.25. How much is it? What's the period?
Well, what is 1.25?
1.25 is our average for the spaceship.
Like, what is it?
Is it 0.2?
It's in AUs.
Oh wait, no, I'm calculating that.
It's the average of the closest is going to be, which is here,
Right.
and the furthest is going to be, which is there.
No, I get that. I'm just like asking, like, what is it cubed? Because I.
Oh, you got to do math. Maddie, do you have a calculator?
1.4.
You got it. It's 1.4, 1.40 or 1.39. It's real close to 1.4. Thank you, Maddie. So what you do is you do this. You take the cube root. Sorry, the square root of 1.25 cubed. The cube of 1.25 is like, it's just under 2, isn't it? Yeah, okay. So it's like 1.9 something. And you take the square root of that and you get about 1.4. So what is it that's 1.4 years? The entire period of the spacecraft's orbit. But do you understand that you don't care for it to come home?
Suicide mission.
You're trying to go to Mars. How long do you think it takes to get to Mars?
A lot more.
Half that time.
So you divide it by
Can't
2.
you see this is half an orbit?
Right?
So divide it by 2,
So
and you're
it's
going to get to
0.7
Mars in 0.7 years. In 0.7 years, multiplied by 12 is about 8.4 months. If you notice, when they send things to Mars, they generally take like 8-ish months to get to Mars. They launch something in July and it gets there in February. That's typical. Yes.
That's so frustrating. It shouldn't take.
Well,
is there no straight shot?
it's a long one. But the straight shot takes more energy.
We don't have that energy.
No.
Don't we have nuclear stuff?
No, we don't. No, I wish we did.
Use nuclear.
Use a
I
nuclear
wish
bomb to
we
launch
did.
it.
Spaceflight.
I wish we had nuclear powered space flight.
Wait, why
I
not?
wish we did. They've kind of worked on it, kind of quit and start back again.
Why wouldn't?
I don't
Because a lot
know.
of people are afraid
People don't
of
like
nuclear
reactors.
signal.
I thought
We have them on Earth.
I know.
Yeah, but like, if we see much or no,
Maybe they'll fall or
people are
something.
paranoid about it.
I thought the probes.
Oh, yeah.
I'll tell you, for example, I firmly believe that the best solution to issues like climate problems and stuff like that is to go whole hog into nuclear power. I think we ought to be building nuclear plants all over the place.
I think that nuclear power
I
is
agree.
so much better than like coal. But
Yes.
also the problem with nuclear waste. I don't
Yeah, what do we do with
Yeah, but there's not that much of it.
Right, it's better. It's infinitely better than
Launch
coal.
the nuclear
Yes.
weapon into space.
But
Yes.
also-
Yes.
I was gonna ask.
Give it to the moon.
I have 2 questions.
Hey, we're getting a little out on here. Let's, Sean, your dad's question, I'm gonna get back up at the board and
Do
do
you
this stuff.
think
Go
that
ahead.
in the foreseeable future there might be a breakthrough that allows us to conserve the amount of like fuel and energy and money that it takes to send it?
Yeah, and one of those things, no, seriously, and no, actually, what Jordan said is completely right. There is the idea of nuclear propulsion, and it's been thought of since the 1940s or 50s. They worked on it some, they've made it some, but they got all antsy and understandably antsy about launching reactors.
Nothing bad happened.
So you can use a nuclear reactor. Oh, let me tell you the best ever idea. Listen to this. Maybe you're going to tell me.
We turn nuclear waste.
I'll tell you. No, listen to this. It's this putt-putt kind of spaceship. When I say putt-putt,
I know what you're talking
I'm
about.
talking about megaton like putts. Because what I'm saying is like, it has a big shield in the back. It's got a couple of names. One is Orion is a code name for it. It's the idea where you have this big, like, blast shield thing, and maybe some cushioning in a spaceship, and you just dump thermonuclear warheads out the back and set them off behind you. Talk about a ride. I mean,
America must have come up with that one.
no, seriously. That idea could get us up to like a pretty good fraction of the speed of light. It's a little bit of a rough ride. But,
People would die
okay.
in that.
Okay, everybody quiet. Actually, you had your hand up, then Jordan. Yeah.
I just wanted to ask, so I've heard about this thorium reactor business.
Yeah.
And like, I've been kind of confused about. So I've been trying to learn about it and research it, and I'm still kind of confused because I'm not that great.
If you have been researching it, you probably already know more about it than I do. What I do know is that, for one thing, I don't think you can make a bomb out of thorium.
Yeah.
But you can use it for a reactor. And the other thing is, even though there's lots of uranium anyway, there's even more thorium.
Exactly.
So it's like a good idea for energy to have thorium reactors.
Right.
Yes.
The bonus of thorium that it's more stable. Like you could easily contain it in the event of an outbreak by just it's like a detachable leg.
That's
Like
what
a
I was
moving
gonna say.
camera.
Oh, like once it comes off, it ain't walking anywhere?
Yeah.
Yeah.
That's weird. Jordan.
Why not do it in space?
Yeah, that's what we're talking
You are, but you got to get it up in space.
We have a space station.
I know, but you got to launch it, and it could fall down.
Right. Why not transport the parts to the space station?
But you got to take the radioactive stuff up. It's not like we don't do that. I'll tell you. Listen, I remember one of my favorite space missions ever was like being protested, and they had to keep people away from the Cape. There was protesters out there. It was in 1997. We were going to launch Cassini, this fantastic mission to Saturn, and it was incredibly successful. It cost like $1 billion. It better be successful. But anyway, Cassini is this mega mission, this big spacecraft going to Saturn, orbited Saturn for years and years and years and years. And it sent the Huygens lander down onto Titan, one of my favorite worlds. And so, like, Cassini was just about the best mission ever. But how do you power something out at Saturn? It's like 10 times as far from the sun as we are, and the sunlight's 100th as bright. You ain't going to do it with solar panels.
So we've already done
They
it.
used, but it's a little different kind. It was plutonium.
Oh, okay.
Nasty stuff, plutonium. It's called a radioisotope thermoelectric generator. I'm glad they made reactors and stuff, because that's where they get the plutonium to make these things. It's the only kind of battery that can do that sort of thing. Solar panels won't work out there, not well enough by a long shot. So we have launched a number of things with plutonium on board. Now, they're in super hardened canister things. Ain't nothing going to happen to them, but in some incredibly extreme, like try to calculate the odds, it's like way down their odds, you could maybe launch it, it could maybe go on the wrong path and come back by Earth and re-enter the atmosphere and burn up the casing and sprinkle plutonium over an area. And what would that do? Probably nobody would know what it did to any particular person, but it might like raise average cancer rates in an area where it went, something like that. So there were these protesters, and I'm glad they failed, and the mission was safe and it went fine. But there's like a 1 in way out there thousands of chance of something, so these questions come up. Yes.
So I wanted to say, like, really quickly, with all of the uranium nuclear weapons that we have, I feel like they would be put to better use if they were converted into reactors. I know that's a thing.
Maybe so. I'm not sure which way those things work, but well, yeah. I mean, I just wish we had more nuclear power plants. 20% of this electricity right here is coming from Plant Hatch and Plant Vogtle in Georgia, our nuclear power plants. Plant Vogel's the only one that my dad worked on both these,
Ooh.
quite frankly, because he worked for Georgia Power for 40 years and he was sort of instrumental in getting those going. If you don't like them, I'm sorry. I like them.
So-
Anyway, Plant Vogtle has a unit under construction, a couple units under construction still. It's the only ones I know of under construction in the United States because they got all antsy about it. Anyway, yes, Gavin.
This is the complete opposite direction.
Oh.
To ask a question.
Okay, and I want to get back to this in a minute.
Yeah.
Okay.
Would it have been possible? What's the earliest point in history it would have been possible with any given materials to send a spaceship? It would send any object into space.
Well, I
The
mean,
Indus River Valley
starting in the
Civilization?
1950s, I think, is about as soon as it was going to get done.
And
it did.
But they had like explosive powered rockets for like before that.
I mean, there's a history of the development that's interesting. Hey,
Wasn't that mantle with the first object we sent into space? 'Cause they were-
the first thing we sent into space, a manhole that something blew up. And I don't know. I've heard that somewhere. I don't know if it really did or not.
The what happened?
A manhole cover, something blew up, and I'm not sure. Back to this. More issues. Everybody listen. Okay, look. So generally it takes about 8 months to get something to Mars. Now you can make it a little sooner if you launch at such a time when Mars is at its own perihelion. It could be a little closer. But the lineup, listen, when you and somebody else are running around a track, you only pass every so often. You sort of know how often this is. I kind of said it. You remember how figuring out the 687 days was from other information, like how often Mars retrogrades?
Yeah.
Mars retrogrades once every 780 days, which is like 50 days longer than 2 years. So the right positioning of the planets comes up just a little longer than 2 years between these things. This is why NASA, China, whoever sending stuff to Mars, do it in sort of seasons. There was a flurry of launches. United Arab Emirates, China, us, India, I think, all launched things to Mars in July of last year. Why? Because that's when the planets were lined up. When's the next time they're going to do it? Like August 2022. You see, there's seasons when the planets line up. Now, one of the problems is if you do this and you want to come home from Mars, you got to do the same kind of orbit to come home. And by the time you get there, if you stay there any time at all, everything gets out of whack, and you got to wait like a year and a half or something before they're back in whack. So the problem with our first missions to Mars that are intended to involve coming back home is you're going to be staying like a year or two until the lineup's right. You don't do like we did with the moon. When we went to the moon, the first time they landed on the moon, Neil and Buzz walked around for about 2 hours, got back in the spaceship and took off. By the time we got to Apollo 17, they were tooling around in a rover for about 2 or 3 days. But they could come home whenever they wanted to. When you go to Mars, you can't come home whenever you want to. You got to stay until they line up right again. So you're going to be on Mars for like a couple of years before you get a chance to come home. Bennett?
So what if you literally just stay there for I'll just say an Earth day? Would it be out of whack?
Well, no, I guess you could do an Earth day.
Like what about
and then
what about,
launch back onto the same orbit. Yeah,
what
you
about
could probably do
4
that.
Earth days? How
It's getting worse and worse the longer you wait.
Do you have plans?
Well, their plans are they're going to stay for a while.
Why?
Because
It took me 8 months to get
it's
there.
like if I drive all the way
Just do it
across the
again.
country, I'm not going to just pop in, say hi, and then leave and drive all the way back. Maddie? Yes, you may.
No, you
Listen, we got 8 minutes to learn a bunch more stuff, so let me get started.
We have 3 minutes. Oh, wait,
We got 8. So, did y'all get this so far?
Yes.
Good, we can do some problems. Now, let me at least introduce you to the next thing. Okay, so, as I make it a little bit darker in here, because I'm going to use board, I'll tell you, you know what? Should I? As I darken things, I'll tell something. So, when I was at Georgia Tech, majored in physics, and I took a class one time called Computers in Physics. You have to understand this is 1980 or thereabouts. And like if you got on the computer at Georgia Tech, you were on literally the computer at Georgia Tech. There was one computer at Georgia Tech. What, everybody all lined up? No, it was called Cyber, and it lived in a building. Mysterious building. Cyber's in that building. Ooh, Cyber's in there, you know. Cyber had tentacles reaching all out over the campus to terminals. And lots of people would all get on Cyber at the same time. I wasn't, now I've been writing a bunch of programs and stuff since. I do a lot of computer stuff.
What, wait, what year is this again?
1980.
Okay.
Or 81, 80 I think. Anyway, so I took this computers and physics course, and I didn't know much. First of all, there were only about 4 other people in my class. And so tiny little class. And the first day of the class is a quarter class, you know, like you know, quarters, like the trimester system, you know, like 3 months. They're like a 3-month long class. Anyway, I get in there and the professor says, our course, we're going to do one problem. One problem. I guess if it's supposed to take the whole quarter, it must be a doozy of a problem. If it's going to, okay, so it is. Here's what it was. Very relevant to what we're talking about. It was, okay, so the moon's in orbit around the Earth, but the sun's over there. And the sun pulls on the moon while the moon orbits the Earth. So it messes with the moon's orbit, huh? It turns out that that problem of having 3 bodies, it's actually called, guess what? This is creative. The 3-body problem. Okay, the 3-body problem, the problem of the paths of gravitating bodies all pulling on each other, as soon as you get past 2 of them, as soon as you go to 3 of them, is unsolvable. It's unsolvable in terms of working it out on paper, and look, here's the answer. It is simulatable with a guess what?
Computer.
A computer. So anyway, the problem was we were going to like, and what's going to happen, I'm going to probably not be able to show you much about the program. Let me set it up though. So anyway, we're going to solve this problem about what happens to the moon's orbit because of the sun pulling on it at the same time and messing with it. Okay, so the professor spent about the first 2-3 weeks of the course doing a bunch of math on the board with a bunch of Greek letters, all Greek to me. Literally, it was like Greek. I couldn't have read my notes out loud because I didn't know the names of some of the letters that looked like, you know, that. It's like, well, it's squared. What is it? I don't know. Anyway.
A very
I would actually look at my notes and say something in the back of my head like squiggly or something like that, you know. But anyway, so I copied, I wrote stuff down on the board. I tried to understand. I was kind of following it, kind of not. Anyway, then we do the part where we go into the computer lab. And now's the part where I start getting embarrassed. Because the other people in there were like proto-computer nerds. You know, like back when there was barely any computers, they were already computer nerds. And they could already like type fast. And I'm like that. Anyway, my first question I had to ask, how do you turn it on? I'm absolutely not kidding. I couldn't find the switch. Everybody else is typing, and it's like, how do I make it do anything? Professor comes over, but, oh, that, oh yeah, that, yeah, sure, yeah, I saw that, right.
Wait, what type of button was it back then?
It was a little, I don't know, you pushed it and it toggled or something. It was a little button on the side, I didn't see it. Anyway, turned the terminal on. And so I'm already kind of embarrassed anyway. We proceed to learn some Fortran, it's a language. And so we're doing this Fortran stuff, and I'm basically just doing everything the professor says to as he says to do it, and basically it's like he's writing a program. I'm not ahead of any, I'm just asking lots of questions. Finally we get the program written. I feel stupid, because these other 4 people obviously know what they're doing, and I don't. And then it's time to try putting the moon in orbit. Now there's no graphics, you don't see it. Like in my program there's going to be graphics. Yeah. But here it was just numbers across the screen. But I knew what the numbers meant. They were distance and direction, you know, vector coordinates. Anyway, so the game was launch them, give them masses, give them velocities, and see if you can get the moon to come back to the same place again. Because if you can get the moon to come back to the same place, you've just found a stable orbit. It was going to be lots and lots of trial and error. And that's going to be the whole rest of the course. We're going to turn in a report at the end of the course about that. So anyway, I keep trying, and the first time I try, here I'm starting to feel a little bit in my element because I knew the numbers approximately. So I put in reasonable numbers, and right away the moon fell into the sun. Well, ow, burned up in the sun. Well, okay, I'll change the numbers a little bit. And the moon went and fell into the sun. I get the moon to do about half an orbit and fall into the sun. And then the only way I could get the moon to not fall into the sun was by making absolutely ridiculous numbers, like making the Earth more massive than the sun. And that wasn't true. The moon always fell into the sun. And then I asked myself a question. I started talking to the people around me. I could tell this fast. Started talking to the people around me. I said, I don't think this is going to work. Yes, it is. I almost got it. Like, dang. Okay. Try the other person on the other side. I don't think this is going to work. Yes, it is. I almost got it. Like, great. And then I asked myself a question. Why doesn't the moon fall into the sun? And then I realized why it doesn't. I might not have time to quite finish this when I get real close. Imagine a movie that's a cliffhanger. You know what I mean by cliffhanger?
Yeah.
It's like something tense and exciting and perilous.
Class on a cliffhanger.
Classically, somebody has just slipped and fallen off the cliff, and the hero or heroine has grabbed them and is holding on tight. That's a cliffhanger. I'll finish this next time. Right.
Tomorrow?
Really?
I'll see you tomorrow.
Yeah.
Continue as you can with the homework. There's going to be something to read. I will post what to read. I will post what to read. I will post what to read.
Do you have a scheduled assessment yet?